Hi, now we will find out components of 4 force in terms of ordinary velocity u and ordinary acceleration a. The 4 force or the Minkowski's force is defined as the differentiation of 4 momentum with respect to proper time. And the differentiation with respect to proper time can be changed into the differentiation with respect to ordinary time by using the relation between the proper time and the ordinary time. So now it is done by compensating dt on numerator and denominator and changing dt by d tau with this expression. And we will have the 4 force as 1 by square root of 1 minus u square by c square into dp mu by dt. Here u is the ordinary velocity of the particle, p mu is the 4 momentum of the particle, t is the ordinary time and tau is the proper time. And by using the expression for 4 momentum p mu, you can write it as mc by square root of 1 minus u square by c square, which is the temporal part, and mu by square root of 1 minus u square by c square as the spatial part. And the differentiation of this p mu with respect to t into this expression will give us the 4 force. And let us, for namesake, for nomenclature, we will call the spatial part as the 3 vector k and the temporal part as k0. And as we did before for 4 acceleration, let us first get the differentials of this temporal component and the spatial component, and then we will substitute back here to get the components of 4 force in terms of the ordinary velocity u and ordinary acceleration a. First we will find out the differentiation of 1 by square root of 1 minus u square by c square. We can adopt the chain rule of differentiation and we can get the differentiation of this function, which will be as seen here in this expression. It is you can take it as 1 by square root of a function, then its differentiation is minus half into the functions to the power of minus 3 by 2 into the differentiation of the function which is inside the square root. That's how the chain differentiation is done. And in this way the differentiation of u square will be now taken as the differentiation of u dot u, because u dot u is nothing but u square. And if you differentiate it by product rule, you will get 2u dot du by dt. And by now, by simplifying this, you will get it as 1 by c square into 1 minus u square by c square to the power of minus 3 by 2 into u dot a. Now we got the differentiation of the temporal part. Now we will get the differentiation of the spatial part as follows. Now here this differentiation can be expanded by product rule, which is the differentiation of first function into the second function and the first function into the differentiation of the second function. You can see that this differentiation is already done as a. You can see the part a is the differentiation of 1 by square root of 1 minus u square by c square itself. We can use the result obtained in a and we can use here. And here for the second term we will change du by dt as a, the ordinary acceleration. It is by definition. So now by simplifying these two, means by taking 1 by square root of u square by c square common out and rearranging the terms, you will get the differentiation of u by square root of 1 minus u square by c square as 1 by square root of 1 minus u square by c square into vector a plus vector u dot vector a into vector u by c square into 1 minus u square by c square. Now we got both the differentiations, which will serve me in substituting and changing this part in this expression of k mu. We will make use of a and b, and we will now write k mu as, by substitution from a and b, as 1 by square root of 1 minus u square by c square into mc by c square into 1 minus u square by c square to the power of minus 3 by 2 into vector u dot vector a and the spatial part as m by square root of 1 minus u square by c square into vector a plus u dot a into u by c square into 1 minus u square by c square. And from this you can take m and square root of 1 minus u square by c square common out, and you can write it into this expression. And this is the required expression. Now we have successfully expressed 4 force in terms of ordinary velocity and ordinary acceleration. Now you can see that we will take out the spatial part of this expression, which is nothing but the 3 vector k. And now we will write it as the 3 vector k equals to m by 1 minus u square by c square into a plus u dot a into u by c square into 1 minus u square by c square. And also by definition we know that the 3 vector k is equals to the relativistic force F by square root of 1 minus u square by c square. And by comparison of these two expressions we can show that the relativistic force F is given by m by square root of 1 minus u square by c square into a plus u dot a into u by c square into 1 minus u square by c square. And the temporal part k0 is m into u dot a by c into 1 minus u square by c square. And you can see that in classical mechanics the Newton's second law can be written in more familiar form as force equals to mass into acceleration. But in relativity this equation for force, for relativistic force, cannot be so simply expressed. You can see by this expression that the force is not just mass into acceleration. Instead, it is a bit complicated, big expression. Thank you.